All right. Done with Instacart for the day. Only made about $100. Actually, no, I made 120 because uh, that first customer gave me an extra $20. Or that might have been yesterday. I do get my days thrown off, thrown off a little bit. So, anywho, I finally have a way of doing this easily. So I'm going to start doing the end of the chapter problems. So I'm going to segregate them into 5 different sections. So starting with number 1, 5, 9, dot, 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 every other odd. Sorry. So it's every other odd. And then 3, 7, 11, dot, dot, dot. Every other odd. 2, 6, 10. Every other even. And it'll be red. 4, 8, 12, dot, dot, dot. And that should be all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, yep, I got all of them in there. So I have 4 different segments. So I'm going to do this in 4 different days. So that way I can say I got all the chapter 1 problems done. So I'm going to try to do that with all of them. And if I'm able to do more, I can do more, but I kind of want to just stick with this so I can work on other stuff because the Bible right now is more important to me. And then the other readings are also sort of like my main thing right now. So let's go ahead and get into it. So the way I'm going to do this is I'm going to flip over to Google Chrome. I already have the book loaded. I have the book loaded on 2 different computers. So that way I can, on this computer, I can flip back and forth so I can take notes and actually do the problems. But I have it on the other computer so I can look at the problem while I'm working on the problem. So yeah, Openstax Chemistry, Chapter 1, end of chapter problems. Number 1, explain how you could experimentally determine whether the outside temperature is higher or lower than 0 degrees Celsius or 32 degrees Fahrenheit without using a thermometer. So, if anybody bothers to watch these, go ahead and pause it and try to answer it yourself. But really, all you need to do is get some water. Since 0 degrees Celsius and 32 degrees Fahrenheit. So number 1, let's get the purple. What happens at 0 degrees Celsius / 32 degrees Fahrenheit? Water freezes. So, get some water. Get some water. And wait to see if it freezes. If it doesn't, not lower than 0 / 32. That's an F. Yay! We did it! Number 5. Identify each of the underlined items as a part of either the macroscopic domain, the microscopic domain, or the symbolic domain of chemistry. For those in the symbolic domain, indicate whether they are symbols for a macroscopic or a microscopic feature. Okay? So, letter A, as a certain molecule contains one atom of H and one Cl atom. And it looks like they're underlining the thing. Yeah, the underlined item. So, the H atom. So, we're going to go ahead and a molecule of HCl. So, if we remember from the acids and bases portion, this is hydrochloric acid. Or, I guess since we didn't say whether or not it's in water, we'll just say it's hydrogen chloride, which would be covalent. And we'll go ahead and do the Lewis structure just to get the practice. So you have technically one here, technically one, or electrons. You got one electron here, one electron here. They're being shared because it's covalent. And then you have the valence electrons around chlorine that hydrogen does not have. So if we remember right, hydrogen should have one valence electron, and chloride should have 7 valence electrons. So, and then the underlined one is this guy. So we're only looking at him. And so, what did it want us to do? Identify each of the underlined items, part of either macroscopic domain, microscopic domain. And then let's look at. So the hydrogen itself is microscopic, or it's going to be. So the molecule is microscopic. So that's like super, super tiny. We're made of trillions of those. Trillions of trillions, or even more than that, actually. Trillions. Yeah, sorry, not trillions. More than trillions. I was thinking cells for some reason. And then the hydrogen atom itself is symbolic. So symbolic is just using the letters. But that's just confusing. But hydrogen itself, the thing that we call hydrogen, is also microscopic. So who knows what they're asking for that? That's such a weird question. Oh, never mind. Looking at the next one, copper wire is underlined. Okay. So it's microscopic domain, or sorry, symbolic domain, and for the symbols. Okay, sorry. I'm so sorry. I misread that. Okay, let's go through that. So hydrogen is symbolic. But belongs to microscopic, or represents. Okay. Okay, that was I went way overboard on that. So that was way too complicated of an answer. So this next one should be pretty quick. It's not symbolic. It's macroscopic because you're using you have a bunch of copper attached to one wire. So C, the bottle contains 15 grams of nickel powder. So that's also going to be microscopic because it's a powder of nickel. So that's a lot. Like one, let's see, if we go to the periodic table, tabler nickel is right here. So if we remember from going in like molar mass and all that good stuff, nickel weighs 58.693 grams per mole. So if you have 1 mole, or sorry, if you have 58.693 grams of that nickel powder, you have Avogadro's number worth of nickel atoms. And I'll show you that real quick. Oops, sorry. There we go. So B. So you have 50 something, 50. 8.693. Grams of nickel per mole. And if you do the Avogadro's number calculation, remember that's times 10 to the 23rd atoms of nickel for 1 mole. Sorry. This is correct, but it's kind of a it might be a little counterintuitive because it probably wouldn't be taught this way. But what I'm saying is that we know that for 58.693 grams of nickel, I get 1 mole. And at 1 mole, so the conversion I skipped was and then this is how I should have done it. Oh gosh, dang it. No, I won't stop the video. I need to pay attention to what I'm doing. Why am I having a hard time with this? I'm That's okay. Duh, I'm stupid. Okay, here's. This is why I'm confused. I'm not used to using a straight 1-to-1 mole to mole thing. So normally you get like fractions of amounts, so it makes it easier to see. Because then when you get your answer, you get your answer. And so here's what I mean to do. There we go. So I'm starting out with this amount. Now I'm going to use the molar mass, which is there we go. Now the grams are cancels. Now I'm left in moles, and then 6.022 E23. Gosh, I have 3. There we go. Okay, there we go. So if I do it this way, this is the way I should have done it. 58.693 grams of nickel. If I start out with that, and then I divide by its molar mass, I get the number of moles of nickel, which is just 1. And then if I multiply it by Avogadro's number, 1 times Avogadro's number is Avogadro's number. 6.022 times 10 to the 23rd. That's 6.022. So 20 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Comma, 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 comma. That is crazy. That's a huge amount in 1 mole. Now, like I weigh 180 pounds. So if I had it's just uncountable. So, anywho, where was I going with that? So I said not to make it complicated. Yeah, I think I was just correcting an error I made. So that's macroscopic. Yep, and then D, sulfur molecule. So that's going to be sulfur with there's 8 of them. Oh yeah, so this sulfur molecule is composed of 8 sulfur atoms. So that looks like this. S8 is a sulfur. Oh, sorry. S8 sulfur molecule. And so it's not asking for just this guy, it's asking for the whole thing. So it's microscopic. So it goes symbolic, but microscopic, macroscopic, macroscopic, microscopic. Those are the answers that I would choose for those four. All right, number 9. What properties distinguishes solids from liquids, liquids from gases, solids from gases? Okay, so number 9. So what did it say? It said solids from liquids, liquid from gas, and solid from gas. And this is actually really easy to do. So let's do, let's draw some beakers. So solids from liquid. I can think of 3 possible scenarios for that. So solid from liquid. I'm going to draw a box. And then in that box, I have 1 cup, 1 beaker, 2 beakers, 3 beakers. Now, I have, let's do 3, I'll just do the liquid the same each time. And then let's do highlighter, same color. Okay. Okay. The solid will be this color. I can either have solid sinks to the bottom, the solid floats on the top, or the solid floats somewhere in the middle. Just kind of depends. However, this one's probably not as likely just because it depends on what the liquid is, really. Because you can add other things and make, you can have multiple liquids in there, changing the property of the liquid, changing its density. So like if I added alcohol to water, it would lower the density of the water and increase the density of the alcohol just by a little bit. And so you get sort of an in-between density. So that's one way of doing it. And then liquids from gas. Switch back to purple. Here. There's only really one way I can think of doing it. We'll do the same liquid as before. Say highlight. And then the gas. I'll have the gas be little red particles. So you have a bunch up there. And then you have a couple bits of gas diffused, or blended in, or mixed into the water. That's why fishies can breathe. And then solid from gas. Yeah, that one's pretty straightforward. You got your solid. And then you got your gas. Just like that. That's how you distinguish the differences between them. So properties, though. What are those properties? So liquids hold their shape along with or hold the shape of the container, the bottom of the container. Solids naturally go to the bottom of the container unless countered by an opposing force. So the density of the liquid could actually push that solid up and make it buoyant. Um, Gas particles are basically moving in straight lines, pretty close to straight lines, until they smack into other gas particles or into surfaces, I guess. Solids are pretty ordered. I don't really know how else to describe it. I thought pictures are the best way. So we'll go ahead and move on to the next one. Number 13. How do molecules of elements and molecules of compounds differ? In what ways are they similar? So molecules of elements mean that. Let me switch back here. So what is an element again? An element is essentially a pure substance, which means that it's made up of the same basic building block. So, but compounds can be pure substances if only that compound exists in solution, which is pretty rare. So, but anywho, um, elemental compounds. Sorry, elementals are molecules of elements. Molecules versus so molecules of elements are made of the same element, and then molecules of compounds are made of two or more elements, but they both use covalent bonding. Yeah, yeah, molecule covalent, based on from what I've read. So that means that electrons are shared. They're always shared. Okay. 1719. How are the molecules in oxygen gas, the molecules in hydrogen gas, and water molecules similar? Sorry, I misread that. Oh, sorry. How are the molecules in oxygen gas, the molecules in hydrogen gas, and the water molecules similar? How do they differ? Well, they're similar because they're all covalently bonded. So I'll show that off. So 19. So we'll go ahead and do H2 gas plus O2 gas gives H2O liquid. But let's do some stoich. Need to balance the oxygens, 2. Now I need to balance the hydrogens, 2. And what does that look like? Plus. Got the lone pairs. I did not draw that right. Hold on. I don't know why I drew diagonally like that. That was really weird. There we go. And that gives you There we go. 2 water molecules. So, how are the molecules in oxygen gas? How are they similar? Covalent bonding, balanced chemical reaction. They both become the same water, like they both become water together. I don't know. And then differences, both hydrogen and oxygen, like the molecules, those are both nonpolar molecules, whereas water is polar. Gases versus liquid. Oh, and then it's 3 things become 2 things. Because it's H and H plus 1 oxygen. Yeah, it's, oh, never mind, sorry. It's 3, yeah, 3 things. 3 become 2. Yep. So, all right. 23. When elemental iron corrodes, it combines with oxygen in the air to ultimately form red-brown iron 3 oxide called rust. A. If a shiny iron nail with an initial mass of 23.2 grams is weighed after being coated in a layer of rust, would you expect the mass to have increased, decreased, or remain the same? Explain. B. If the mass of the iron nail increases to 24.1 grams, what mass of oxygen combined with the iron? Okay? That's fun. All right. So, 23. So I got this. So A, 23.2 grams. So let's say I got this little rod of iron, and it weighs 23.2 grams of iron. But it rusts. What is rust? Well, they said it. It's iron 3 oxide. So you're going from Fe, and I'll say it's a neutral charge, 0. That's if there's no charge written above something, it's implied 0. Unless it's got a plus or a minus, obviously. But it's a neutral charge. Iron is going to go to iron, FeO3. So each of these has a -2 on it, formal charge, if you remember that. That means it's -6 formal charge. So that means this has to have a +6 formal charge. So that means there's 2 of them. Which means you're adding oxygen, so plus O2, 2, 4, 3. 6 oxygens, 4 irons, 4 irons, 6 oxygens. So that's basically what that equation looks like. We're going to add 3 oxygens to it. So, A, you would expect the mass to increase. And then part B, it increases to 24.1 grams. So, how much oxygen is added? Well, that's pretty straightforward. Conservation of mass, it's not going to come from anywhere else. So, that means, let's go ahead and get that out. 23.2 grams X. So X plus 23.2 grams equals 24.1 grams. Little algebra, subtract 23.2 from each side. That becomes 0, and this becomes 9, 0, X. X equals 0.9 grams. And that's how much oxygen you have. O2 added. Cool. 27. Classify each of the following changes as physical or chemical. Condensation of steam. So condensation of steam is H2O gas to H2O liquid. Well, didn't change its chemicals at all, so physical. Burning of gasoline. Well, that's going to be CX HY OZN Q. And I think, what's the other one? There's like 5 main ones that I see, like sulfur. We'll just do it like that. This is basically the generic form for a generic combustion reaction. Actually, I'm just going to get rid of those. Let's just do these ones for now. This is the simplified version. There's always going to be trace things in when you do stuff. Oops. And then this could either be solid, liquid, or gas. Depending on what it is. Gasoline is a liquid though, so it's an L. So that's what that looks like. That's definitely a chemical reaction. The souring of milk, well, it's still liquid. Well, it's a little bit of both actually, because souring of milk tends to create solid chunks. So, although that's not technically part of the milk anymore. Dissolving sugar in water, that's a physical change. You're just separating the sugar lattice in between the water molecules. And then melting of gold is also, that's just gold to gold. So, also physical. 31. Explain the difference between extensive properties and intensive properties. So usually when I think extensive, I think external. Intensive, I think internal. So let's make sure I have that correct. Oh, I keep forgetting to go back to the... Sorry, I keep forgetting to go back here. So the last one, classification of each of the following changes as physical or chemical. Physical, chemical, and physical as a consequence. Physical. All right, sorry, 31, explain the difference between extensive and intensive. So if I go up, those are actually defined. Property of a substance that depends on the amount of the substance. So amount of the substance means it has nothing to do with the internal properties of that substance. It's essentially multiplying whatever the properties already are. And then intensive, here, property of a substance that is independent of the amount of the substance. So if you change the substance, you change the properties. So it does depend specifically on that substance itself. On basically, I guess you could call it like the base unit of the substance. So what extensive is how it affects. No. How would I describe that? What would be a better way to describe that? Let's see. Yeah, so it has nothing to do with the property, or the properties of the substance itself. The property is already defined by the substance, and so you increase the substance, it increases that property's effect on the external environment. And then intensive is just based on what it is. Yeah, so I don't think I can explain it any simpler than that. Okay, next one. Oops, too far. It's 31. 35. Is a meter about an inch, a foot, a yard, or a mile? It's about a yard. A meter is roughly 3.3 feet, or 3.25 feet. 3 feet, 3 inches, roughly. Okay. 39. Give the name of the prefix and the quantity indicated by the following symbols that are used with the SI base units. All right. A is C, so that's centi. B is little d, so that's deci. Actually, I'll go ahead and write those down. So prefixes, prefixes, yeah. So C, centi, D, deci, and then cap G, giga. Oh, and the quantity. So 10 to the minus 2, 10 to the minus 1. I think this is 10 to the 9. K equals kilo. That's 10 to the 3. M equals milli. 10 to the negative 3. N is nano. 10 to the negative 9. P pico. 10 to the negative 12. And then cap T, tera. And that one is, oh, sorry. No, I think I got giga wrong. I think giga is something else. Kilo, mega 6, tera. I think it might be 10 to the 9. Giga 10 to the 12. Let's look at, let's just make sure real quick. Let's go to SI prefixes. Just want to be sure real quick. Oh, I got it backwards. Giga and tera are opposite each other. Nine. I had that right the first time. 12. Yeah. And then cap P is peta. That's so crazy. All right. Those are the prefixes and their amounts. Okay, that was 39, so 43. I'm not going to do that one. I don't feel like looking at any simulations. So 47. Indicate whether each of the following can be determined exactly or must be measured with some degree of uncertainty. The number of seconds in an hour. Well, an hour is defined as 24 hours. Sorry. An hour is defined as 60 minutes. And 60 minutes is defined as 60, or sorry, a minute is defined as 60 seconds. So those are whole numbers, so that's exact. The number of pages in a book, well, it would be really weird to measure a book's number of pages with a degree of uncertainty. So yes, the number of pages is exact. Number of grams in your weight is going to be inexact because scales are always calibrated to within a range of values. The number of grams in 3 kilograms, well, if it's 3 kilograms, there's 1,000 grams in a kilogram, so that's a whole number conversion, so that's exact. The volume of water you drink in one day. That would be inexact because temperature affects volume. So like holding the cup, you'll add some of your temperature of that in there. So you can't possibly know exactly what volume it is. The distance from San Francisco to Kansas City will also be inexact. You'll have to be to some uncertainty because you'll use some sort of scale to measure it. 4951. Round off each of the following numbers to two significant figures. All right. Two significant figures would be at the 3. So that would be 0.44. All right. B. The second 0. The first 0 is the second significant figure. So 9.0. The 7. So 27. Or 27 point. The 3. So either 130 or in scientific notation 1.3 or 1.4 times 10 to the 2. So stops at the 4. So 1.5 times 10 to the negative 3. 0.45. All right, number 55. Is that right? Yeah. Consider the results of the archery contest shown in this figure. Which archer is most precise? Which archer is most accurate? Who is both least precise and least accurate? So the most precise one is Archer X because all of their shots were the closest to each other, and that's the definition of precision. Accuracy would be Archer W because all 4 points are close to the target value. And then Archer W also is, he'd be most precise, most accurate. I would say Archer Y is the least precise and least accurate because, one, all 4 of their points are all far away from each other, even though Archer Z also is, but not one of the shots hit the target, so it is not accurate at all. Okay. 559. The label on a soft drink gives the volume in 2 units, 2 liters and 67.6 fluid ounces. Use this information to derive a conversion factor between the English and metric units. How many significant figures can you justify in your conversion factor? So you can really do it 2 ways. I feel like having a number larger than 1. So I'm going to do it this way. So the conversion factor for number 59 can be written 2 ways. It can either be written as .0 liter over 67.6 fluid ounces, or 67.6 fluid ounces over 2.0 liters. And so since I want the larger than, or number larger than 1, I'm going to do this one. So that's basically 3 points. Trying to think of what the. Sorry, nope, I got that wrong. I'm just going to do it the long way. Oh, come on. Three, 6, 7, 3, 6, 1, 6, 8. 33.8. So 33.8 fluid ounces per 1 liter. And significant figures will be rounded to here. So 34 fluid ounces per liter is the conversion factor. All right, so 63. How many milliliters of a soft drink are contained in a 12-ounce can? Oh, well, we just did a conversion factor, so we'll do 67.6 per 2. Actually, it doesn't matter. 33.8 per 2. I'm going to just use an unrounded. FLOZ per liter. And we have 1,000 milliliters to liters. Well, 2 liters is basically saying 2,000 milliliters. I'm sorry. Never mind. I keep screwing up. I keep putting the wrong numbers in. Dang it. I'm confusing the heck out of myself. Okay, here we go. 12 ounces, 33.8 ounces per 1 liter. 1 liter, 1,000 milliliters. And there you go. There's your answer. So that's almost like saying, I'm just going to say that this here is like saying 12 divided by 36, which equals 1/3, times 1,000 equals 3,000 over 3 equals 1,000 milliliters. It's roughly 1,000 milliliters. Because actually, 16.9 ounces is 500 milliliters, which is 16 ounces. 16.9 ounces is 500 milliliters. So it's just slightly less than that. Oh, wait. Nope. Fuck. Why do I suck at doing math? Why did I say 3,000 over 3? That's 1,000 over 3. That's 300. Gosh, I'm so annoying. That makes sense, though. That's close. It's 300. This is just my first time doing this and getting used to doing this again, so I apologize for all of the errors I am making. This is a work in progress. Okay. 67. Is a 197-pound weightlifter light enough to compete in a class limited to those weighing 90 kilograms or less? I'm just going to do 90 times 2.2 because that's pretty close. 2.2. So that is going to be 0.2 times 90 is 18. And then that's there we go. And then that's 180. All right, 198. And what did it say it was? 197? No. Too fat by 1 pound. 71. Scientific experiment exponential notation to express the following quantities in terms of the SI base units. Okay, so this is, so there's 0.13 grams, 232 gigagrams, 5.23 picometers, 86.3 milligrams, 37.6 centimeters, 54 micrometers, 1 terasecond, 27 picoseconds, 0.15 millikelvin. Okay, 3 grams. So I want to move the decimal place over 1 to the right. So it's going to be 1.3 decigrams. Yeah. Okay, so 232 gigagrams. And I want to turn that into, let's move over twice. I don't actually know what 2 less than giga is. I only know what the 3s are. Oh, well, here's what I could do. Well, that's like saying times 10 to the 9 grams. There we go. And then if I move the decimal over place over 2, it'd be like, what, 2.32 times 10 to the 7 grams? Sorry, 10 to the 11 grams. Okay. 5.23 picometers. Pico. 10 to the negative 12. So 3 times 10 to the negative 12 meters. That's it, actually. Oh! Wasn't asking for the units. I got myself confused there. 86.3 milligrams. That's 86.3 times 10 to the negative 3 grams. And that's 8.63 times 10 to the, it's going to the right, so 10 to the negative 2 grams. Okay. 37.6 centimeters, 37.6 times 10, 2 meters over 1, 3.76, 10 to the 1 meters. $54 micrometers. 54 times 10 to the negative 6 meters. 5.4 times 10 to the negative 5 meters. 1 terasecond. 1 times 10 to the 12 seconds. 27 picoseconds. That's 27 times 10 to the negative 12. 27 times 10 to the negative 11. Sorry. Yeah, to the negative 12, so negative 11. 2.7. Okay. 0.15 millikelvin. 0.15 times 10 to the negative 3 Kelvin. 1.5 times 10 to the negative 4 Kelvin. Okay, 75. A long ton is defined as 2240 pounds. What is this mass in kilograms? About 1,000. And I'll let you figure that out. 79. A chemist's 50 trillion angstrom run would be an archaeologist. I'm not going to look at that because I need to look at another exercise. 83. A chemistry student is 159 centimeters tall and weighs 45.8 kilograms. What is her height in inches and weight in pounds? Those are just conversions. You guys can do that now. Calculate the density of aluminum if 27.6 centimeters cubes has a mass of 74.6 grams. So density, mass over volume. So it's going to be 74.6 grams over 27.6 centimeters cubed. About equal 75 over 25, 3. Roughly 3 grams per centimeter cubed. Okay. 91, calculate these volumes. What the heck? All right, what is the volume of 25 grams of iodine with a density of 4.93 grams per centimeter cubed? The density equals 4.93. So it's the volume. So we got to rearrange the equation. Trying to find the volume. So multiply both sides. Most times V times V. You get VD equals MV over V. Those cancel. And then divide by D, divide by D. And then you get an arrow. V equals M over D. Okay? 25 divided by 5 is 5. Cool. And then I think this is probably one of the later one. What was that? That was 91. 95. Oh, where's the cursor at? Jeez. 95. Convert the temperature of the coldest area in the freezer, negative 10 degrees Fahrenheit, to degrees Celsius and Kelvin. Okay. Trying to remember right. It's degrees Fahrenheit equals I have 9th degree C over 2. Let's see what we get out of that. I'm just going to see if I remember it. So negative 10 minus 42 times 9 divided by 5. Nope, that's not right. Let's try it. Degrees C equals 5 over 9 degrees F plus 32. $50 divided by 9 plus 32. Nope, that doesn't seem right. Okay, I don't remember what it is. Let's zoom up. So T degrees C equals 5 over 9 times degrees F plus or minus 32. Here we go. Okay. So minus 10, minus 32, 5 over 9. That's minus 42 times 5. It's going to be 20-something degrees. It's going to be between 180, which is 20 degrees Celsius, and 270, which is 30 degrees Celsius. No, I guess, no, sorry, I'm so stupid. What am I doing? Why did I say that? I think it's just because I'm just multiplying by 9. I don't need to say that. That's not true. That's not how that works. But it's gonna be close to that 210 mark, so about 20-something degrees. And then 99. The weather in Europe was unusually warm during. I keep forgetting to switch to this. Dang it. The weather in Europe was unusually warm during the summer of 1995. The TV news reported temperatures as high as 45 degrees Celsius. What was the temperature on the Fahrenheit scale? High. I think I'm going to end up just redoing this one. No. Now let's finish strong. I'm frustrated. Degrees F equals 9 over 5 degrees C plus 32. Is that right? I'll have to write these down next time so I don't go too far. Oh my gosh. Yeah, okay. Sorry, I'm frustrated. It's been a long time since I've done any math like this, so I'm going too fast for myself. I used to do these equations really fast, so I think that's why I'm trying to go too fast. Trying to impress the ladies. Just kidding, I can care less about that shit. So we say 45 degrees Celsius. So that's 45 divided by 5, 9, 81 plus 32. 113 degrees Fahrenheit. That's it. Calling it a day for that.